just so we have this go back. I think I might do some Excel stuff today. All right, so we started looking at Excel a little bit last class. I don't think we worked through these examples. I believe we went through and did the rainfall ones, right? But I had some examples just to get a little bit more practice with temperature as well, right? So we can break temperature down by different months. If we work through these, remind me, and we don't have to go through them again. I'll probably go through them pretty quickly, but just wanted to point out a couple of things. So let's say I've got temperature in June. And on average, it's 70.75. No, it's not. Yeah, it is. I got it right. And the variance is 6.3. What's the probability the average temperature in June is greater than 71.4? So this is where drawing it out, I think, always just helps at least make sure we're not making egregious errors. So here's our mean. The value we're interested in is 71.4. And we want the probability of being greater than that. So right away, we know this probability has to be less than what? Yeah, right. The area to the right of the mean is 0.5. So we want something smaller than that. So right away, I'm thinking it's either going to be A or D. Right? From there, what we're going to do is convert this into a z-score. Right? How do we do that? We take the value we're interested in, we subtract that mean of 70.75, and we divide by 6.3, right? Now, what do I need to divide by here? Yeah, so I need to divide by the standard deviation. I was given a variance, so I need to make sure I take the square root of that. So if I'm looking at this, I don't know the exact, it looks like it's less than a standard deviation away. Sure enough, 0.256 would be our z-score. Not 6, 9. Yeah, 2.259. Now, we probably aren't the most frequent or most kind of, we've been using this a lot, so we're not super familiar with kind of different values for z. But we started thinking about like 1 standard deviation is kind of far away, but not too bad. 2 standard deviations is really far away from that mean. So we start getting, so it's very unlikely we see something that far away. At 0.25, well, that's pretty close. And I didn't draw it to scale, but right, 0.25 is pretty close to 0. So that area is probably going to be a little bit closer to 0.5 than it is to 0. So if I was guessing, looking at this, I'm probably going to go with the one that's closer to 0.5 than, versus the one that's closer to 0. But if we look up 0.259 in that z table, the area to the left of it is 0.6, right? So the area to the left was 0.6026. We got to use our table. Now, what's going to be one problem if I try to look up 0.259 on the table? I can only look up 2 decimals, right? So I'm always going to have to round my z-score to the second decimal point. So here I would go 0.26. So 0.2, and go over to the 0.06 column. That probability I'll find is 0.6026. It gets a little bit tricky when we have z-scores less than 1, because now we've got like, oh, maybe I confuse this with a probability. This is not a probability, right? This is my z-score, 259. So I wanted the probability of saying that original x value or greater. So I'm going to have to then subtract the area to the left of that z-score from 1, and that will give me the area to the right. Question. Okay, and I think we might have this one, but it's kind of a similar idea, right? The only difference is, right, we've got some different values. So if you want to go through another one like this, I'm going to kind of save this one for you. But once again, if we just draw it out, remember the principles of what we're doing, you might be able to take a pretty good guess. Now, first of all, if I'm interested in the probability, which one of these can I rule out right away? Yeah, 2.73 doesn't make a whole lot of sense if I'm looking for the probability. So the average temperature was what? 28.89. I want to know the probability I saw 42.85 or greater. Now, initially I might think, well, this is so far away from the mean, like that probability has to be pretty close to 0, right? But you know, if I think a little bit harder, well, what's the standard deviation here? It's about this, what, square root of 26.16. So it's going to be just over 5. So I still am pretty far away. I'm like more than 2 standard deviations away. I'm guessing if we calculate the z-score, I'm guessing it's 2.73. I'm guessing that's why that's one of the answers. Right? But, you know, once I figure out that this is a pretty high z-score, well, it'll be a little more complete here. So once I convert that value into z-score, well, I'm almost 3 standard deviations away from the mean. That's pretty far. It's probably going to be that this probability is pretty close to 0. Sure enough, if I look it up, you know, or if I look up any of these possible options, the only one that's close to 0 is B. In fact, why do I know without even looking this up, where I don't really have to guess that the answer has to be B?
Because C and D are both bigger than B.
Now, when I draw this out, it's nice to kind of, a nice visual to remind me, oh yeah, the area to the left and the right of the mean is 0.5. I'm going to want something that's much smaller than that. The only thing less than 0.5 up here is 0.0032. Okay. Any questions on that? I mean, I didn't, you know, pull the table up and look these up for it. I want more so to kind of go through these principles. Okay. All right. So we'll talk about the inverse transformation. And then I think we'll jump into Excel for a little bit. So we can find the probability of being above or below certain values, turning normal distributions into standard normal distributions. But what if I want to work the other way around? So let's say I start out with that z-score formula. Let's say I'm told the area that I want to the right. So this might be something like, what value would be the 90% cutoff for a certain test? Like what test score would be the 90% cutoff? So why could I do something like that? Well, if I rearrange this equation a little bit and think about, I'm trying to find the x value that gives me 0.9 below it. I'm looking for like that 90th percentile cutoff, and then 0.1 above it. Well, if I'm thinking about my z-scores, I know that if I had the mean and the standard deviation, I could turn this into a z-score. But I'm working backwards. So now I know the area that I want to the left of my z-score. I don't know what that z-score is, but I know it's the z-score that gives me an area of 0.9 to the left. Now, this doesn't have to be 0.9. I'm using that as my example, right? The 90% cutoff. So as long as I know kind of the area I want to the left of my value, 0.9, I can work backwards and find the z-score that would give me that 0.9 in the tail. Once I have that z-score, and I know the mean and the standard deviation of that variable, I can then back out the value for x that would have kind of given me that z-score. But I don't know x initially. I only know the area I kind of want the tail. So essentially working backwards. So what's that going to look like in practice? So put some numbers in this. I think I did the 90th percent cutoff here, right? Yeah, top 10%. So kind of nice and easy here to match this up with this example. Right? We know that the mean should have a z-score. So the mean here is what, 72? The mean should have a z-score of what? Yeah, if I subtract, remember the z-score equation was take the x value, subtract the mean. Well, if I subtract the mean from the mean, I'm always going to have to do the z-score of 0. So now what I'm going to do, I've also got my standard deviation, I think up here is 8. How can I find this z-score? So I'm going to go to the tables. If I have them pulled open, do I not? Apparently I don't. I know I used them earlier. There we go. So what I'm going to do, instead of looking up my Z value and then finding the corresponding probability, I'm now going to look for my probability of 0.9. So I'm hunting through here. Looks like smaller and smaller and smaller. Oh, I can't get exactly 0.9, but I know that it would be in between these two values. Okay. So 0.9 is in between these two values. So I will then go over and figure out what Z-score corresponds to those probabilities. So I go over 1.2 and I scroll up 8 and 1.29. So the Z-score that gives me approximately 0.9 in that to the left of it is going to be somewhere in between 1.28 and 1.29. I probably have to go out to like a third or a fourth decimal to get the exact value. So in practice, when we're doing this by hand or when it comes to the exam, anytime that we have this table and at the second decimal, we're going to be in between two values, always take the greater of the two. And if they're negative, take the larger absolute value of the two. So we'll kind of use that 1.29. That's that Z-score that gives me 0.9 to the left of it. Well, now that I have that, if I go back, notice all I was doing to get that inverse transformation formula was rearranging this. So I multiply both sides by the standard deviation. I add the mean to both sides. And now it's just a matter of plugging in my value, right? 72 plus 1.29 times 8 will give me that test score that would be the 90% cutoff. Questions on that one? Yeah.
Why would you say like the Z-score was very slightly like the mean minus itself?
Oh yeah, so this is the equation I have for the Z-score. If I wanted to turn the mean into a Z-score, well then the value of X I'm interested in is the mean. So the mean minus the mean would always give me a Z-score of 0. So anytime I'm thinking about the mean of my original variable X, if I did, we don't have to turn it into a Z-score, but if I did, I just mentioned these things so we can be really familiar with the traits and properties of this different issue. Questions on that? So where are we at? There we go. So we worked through this one together. I'm going to have you guys work through one on your own. So let's say I have a very similar setup, right? Same test score, so it's got the same mean, same variance. But now I want to know what is the lowest score that would be in the bottom 40%. So here's the lowest here. Wait, not the lowest score. I want basically, I think that the way I said that is a little misleading. Basically, what test score would be the cutoff such that if I'm looking at that test score, it's the cutoff for the bottom 40%, right? So I want you to find the test score that's the cutoff for the bottom 40%. And try to work through this one and actually come up with it. But we actually, by process of elimination, could probably figure this one out relatively quick. But I want you to get used to looking up the Z-score that gives you that 0.4 in that lower left tail, plugging it into that inverse transformation formula. You know, if you don't want to use the inverse transformation formula, you can just plug things into the Z-score equation and then solve for the X that you don't know, right? Like if I plugged in Z, plugged in the mean, plugged in the standard deviation, and now I have one equation, one unknown. Either way would get you to the correct answer.
Okay.
That's what I did though. That's my.
Okay.
Okay, maybe I forget. Congratulations.
All right. If you haven't gotten an answer in, let's take your best guess here and we'll kind of go through it. 12 of us. I think there should be 4 options. Should get 2 more of you that I didn't get recorded. So I'm going to close it out here. So make sure. There we go. All right. Okay. So first of all, I'll make this a little bit prettier. So what I'm looking for, I've got this normally distributed variable, mean of 72, variance of 64, so a standard deviation of 8. And I said, I want to know what this x value is. That gives me an area of 0.4 in that lower left tail. So when I'm looking up that z-score, right, I want the z-score that would give me 0.4 in that lower left tail. Okay? We're all okay up to that point. That makes sense. So what do you know has to be true about the sign of that test score? Yeah, right. If the area I want in the tail is only 0.4, that can only come from a value that's below that mean of 72. So right away, I know that whatever x value I'm looking up is going to have to be a value to the left of the mean. I mean, technically, all 3 of these are to the left of the mean, right? These don't make any sense in terms of being a test score, right? That's the 40% cutoff, right? So just by looking and thinking about, oh, I want an area of 0.4 in that to the left, or that cumulative probability to be 0.4, I have to be thinking about a value that's below the mean. It's going to help us prevent us from making some pretty easy mistakes later on when I actually look up this z-score. So I actually look up 0.4 in the table, right? So I'll pull open that table real quick. So 0.4, I know it's going to be a negative z value. Looks like kind of in between these two. So negative 2. Scroll up here. Negative 2.5 and negative 2.6. So like I said, we'll use the greater and absolute value of the two since, oops, come on. All right, since this one is negative, we're going to take the absolute value as the greater of the two. So negative 0.26. I'll then use that z-score, right? So I have my transformation formula. All I'm going to do is plug in that negative 0.26, plug in 8, plug in 72, and I should get approximately 69.92. Now, one of the things there is I can check a really easy mistake, which is maybe I accidentally like add this up. Like I forget there's a negative sign here. And I would have gotten the 74.08, I think it would have been, right? But then I quickly remember from my visual, oh, well, I'm obviously going to be looking for something that's below the mean. 74, that doesn't make any sense. I go back, forgot the negative sign of my z-score. Okay. Any questions on this one? Unless you guys are working on it for a while. So if you ran into anything that you kind of ran into a roadblock or something that you have questions on here. No, it's only gonna get harder. Okay. All right, so I think here we're gonna take us aside and go to Excel. So last class we had kind of looked at this, and we had built this out for every month. I kind of showed you how you could really, make this for every month instead of just 3. But just for the sake of kind of looking at things, we'll go back to those original 3 today. And I'll show you some things I didn't show you. That is not what I wanted to do. I'll show you some things I did on Monday. So I think up to Monday, what we had done was we had found the probability, we turned certain values into z-scores. We then found the probability that we were less than that z-score, kind of acting similar to the table. And then we also did, well, I could just do 1 minus to find the probability that I'm greater than a certain z-score, right? And the way that we found these probabilities was using that norm.s.dist function. We said all we have to do is put in the z-score. We're interested in finding the probability of seeing that z-score or anything to the left, right? The cumulative probability. And then so when it says cumulative here, comma, we always put a 1, right? I said when you put a 0, I don't, if I put a 0 in here, let's see what it does. Right? I mean, I don't, it's not telling me the probability of one specific value. Right? It doesn't really make a whole lot of sense. It's breaking it down to intervals and then calculating the probability. The probability of any one value should be 0, right? So we just ignore that part of this function. We're always going to just use it like we would the table, like that we have by hand, and always make that cumulative comma 1. Okay. So this is kind of where we left off last class. I think we maybe had some different cutoff values, but nothing really, that doesn't really matter. So one thing we can also do is instead of calculating the intermediate steps, we start to, as we kind of progress through the functions in this class in Excel, you'll start to see they become more and more black boxy. By black box, I mean like I put something in here and it comes out the box and I don't know what happened in the box, but it's like changed whatever I put in, right? So these functions, we can't see what's going on behind the scenes, right? But if we give them some inputs, they'll spit something out at us. So here, if we don't want to calculate the intermediate step of the z-score and then use the norm.s.dist, we can just use that norm.dist function. So not norm.s, or that was standard normal. If we use the norm.dist, what we're telling Excel is, hey, this variable is normally distributed. I want you to convert it into a standard normal distribution, look up, calculate the z-score, look it up in the table and tell me the area to the left or the probability of seeing that z-score or anything below it. But it's going to do all that behind the scenes. Right? So the first thing we tell it is, okay, what value are you interested in? Well, here I'm interested in 71.4 maybe, comma, well, what's the mean? Well, here I was looking at June temperature. So the mean I had up here, comma, what's the standard deviation? I believe the second row was variance and the third row we had was standard deviation. So I select that June standard deviation, right, and their temperature. And then just like before, that fourth thing, we'll just make it a comma 1, telling it to make it cumulative, give us the cumulative probability. So what this function is going to do is it's going to take 71.4. It's going to subtract the mean, divide by the standard deviation, right? Get that z-score, look that z-score up in the table, or essentially really what it's doing is it's integrating that probability density function up to that z-score, right? Giving you that cumulative probability and spitting it out at you. So if we did the intermediate steps correctly, we should get that same probability of 0.58 here, right? It's just we've avoided all of the steps in between. Okay. So we can we don't have to calculate the z-scores. We can kind of use that norm.dist function, which will do it for us behind the scenes and get those same probabilities. Okay. And if I want to do, the probability of being greater than a certain value, well, same kind of idea. I can just do 1 minus here, right? Okay. And I'll save this and repost this in the analytic data file.
Oh. There we go. All right, I guess I'll be working on this later. So any questions on that before we keep going here? Okay, what if we wanted to know what, how do I write this? So what temperature would kind of be the 90, well, let's do the 80th percent cutoff. Just choose some different numbers, right? So what temperature would be greater than 80% of the other possible temperatures I could see? So kind of think about it here. We're working with the inverse. I know the area to the left of this X value I want is going to be 0.8. Okay. So what X value is the probability of seeing that X value less than or equal, sorry. What X value is the probability of seeing that value or less equal to 0.8? Okay. So that's what I'm looking for. I don't know it, right? Well, I'm just gonna, for a reference, kind of put that 0.8 over here. What I can use is norm dot, what do I want to show you first? I'll show you both ways to do it. So the first thing that we're going to want to do is look up our z-score, right? So if we remember, right, we had z times standard deviation. That was kind of our inverse transformation formula. So I need to find that z-score that gives me 0.8 to the left. So the way that I'm going to do that, I want to label this so that it's a little bit easier. So first I'm going to find that z-score. So I'm going to use the norm.s.inv. Okay. What norm.s.inv does is it says, okay, look, Excel, use a standard normal distribution, right? Norm.s. Look up this probability that I want in the left tail, or look up the cumulative probability that I'm telling you, right? And I don't know why I did this. I put 0.8 in there. I put it up here for a reason. Right? So I can use that cell reference, okay? Once I have that z value, well, now it's just a matter of, if I want the probability that, I want to find the x value, well, now it's just take my mean. I have my mean up here for June temperature, comma, oh, not comma, I'm getting all mixed up, plus the z-score, which I found right here, multiplied by my standard deviation. So 72.97, or just under 70, or just, yeah, under 73 degrees, right, would be the cutoff for the 90th percentile of June temperature. Okay. Now, I could have also skipped these intermediate steps. So just like when we had norm.s.dist, and I said you can skip calculating the z-score by just using norm.dist, we also have norm.inv. Okay. So this norm.inv, you still tell it the area you want to the left, right, or that probability that you're interested in, comma, what was the mean for that variable, comma, what was the standard deviation for that variable. And now, if what I'm telling you is correct, this should spit out at you that same 72.97 value. It's just skipped it. It doesn't show you that intermediate step of calculating the z-score, right? So sure enough, they get the exact same value, okay? So kind of the ordering there for that norm.inv function is probability, mean, standard deviation, are the three things you have to tell it, okay? So then what it does is it looks up that probability in the table, finds the corresponding z-score, takes that z-score plus the mean and standard deviation you told it, plugs it into this inverse transformation formula, and spits back out at you that x value, okay? So norm.s.dist and norm.s.inv are just like you're looking up z-scores in the table. Norm.dist and norm.inv are calculating things behind the scenes and then looking those values up in the table for you. You just don't see, what those intermediate steps are. Any questions on this? You know, once I have this set up too, I'd be like, okay, well, what's the 90th percent cutoff? Automatically updates. Well, what would the cutoff for the bottom 10% be? Oops, I don't want to put it there. 0.1, right? I can kind of get these, get these updated pretty quickly. Okay. We okay with this? I'm feeling like a low energy today. I'm not getting good vibes from you guys. So, all right. I shouldn't say I'm not getting good vibes, but I'm getting like dead vibes. like you guys are tired or something. So we're almost there, right? We're almost there. We need to recharge. All right. So I have another tab here where I did kind of the one that we did in class. Like you could work through that and produce the exact same answers. And I'll save this. I'm not going to close this file to figure out why it's not saving after class today. And I'll kind of repost in the Indiana weather data file to kind of include some of this work down here as well. Okay. So I know that on Friday, we're going to go through some more difficult stuff. We got 13 minutes. Maybe I'll show you some more stuff in Excel today. So one thing that I think is kind of cool, and I'll start to try to use Excel a little bit more to kind of show you not only the power of Excel, but to try to really hammer home some of the things that we're going to be talking about and giving you a data visual. Okay. So that table, right? We can actually reproduce it, right? So I want to show you a little bit of the power of Excel. I wouldn't expect you to ever do something as complicated as this in this class. But notice if I've got these different values, right? I kind of keep like, I'm trying to build this table, right? So here's my first decimal. Here's my second decimal, right? Really all we would be doing for every z-score, if we want to find the area to the left of it, what function could I use in Excel? Well, we were just talking about, if I just use the norm.s.dist, all I'm doing is telling it a z-score, and it's telling me the probability I see that z-score or anything to the left. So if I really wanted to, I could like do something crazy. Like let's say I go -4, -4.01, -4.02. And then I kind of fill my series here. Hopefully it jumps out. That started jumping up by 1. I can do a fill. I can do a series. I can go up by 0.01. And then if I use that, start here, norm.s.dist, all I would do is tell it that z-score, (1), and it's going to give me the area to the left of all these z-scores. I could find this for any z-score imaginable, right? So I had this idea of like, well, you could actually build your own z-score table. Like if I was really mean, I could like ask you guys to do this, but I won't. So notice all I'd be doing in each one of these cells is using the norm.s.dist function. So for instance, here I would take -4 plus 0, right? So this I would find the probability of seeing a z-score of -4 or lower, and then -4.01. So this is the probability of finding a z-score of -0.401 or lower. If I'm thinking about the cell down here, norm.s.dist, and then put 0.2. So this is the probability of seeing 0.20 or lower. But I don't want to have to type this in for the entire, combinations of these first and second decimal points. So what you could actually do, right, is use a combination of if statements. So we haven't really played around with if statements too much. I'll probably start using them a little bit more here in the kind of the latter half of the class. But all you're really, and the reason why you had to use if statements here, because what I did was I simply took the first decimal and like added my column heading. The problem was if it was negative, I actually needed to subtract it, right? Because I'm looking at like, it's supposed to be the second decimal. But basically this combination of if statements, and then you can also freeze cells, but only freeze one part of it. So notice here, I froze the column, but not the row. So when I copy this down, it's going to keep using that same B value, right? B1, because I froze the row there. But as I copy it down, it allows the rows in A, right? It keeps A the same, but it allows the rows 2 through whatever to update. So we won't ever really exploit that in this class. But if I was like an accountant, I don't know what you guys do in accounting, but if you should be using Excel spreadsheets at some, I mean, I think I heard Professor Stanfield mention that he has you guys, I don't know if you guys have him, but he has his students use those. There's a lot of stuff in accounting where sometimes you might want to freeze the column, but not the row to kind of make your life easier in terms of how much typing you have to do. So that's kind of an example of that here. And then the if statements, I don't think I've shown you one before. I shouldn't call you people out, sorry. I'm going to. Who used the if statement in the last Excel one? Yeah, Harrison, I should remember that. Yeah, I loved it. I was like, I got happy seeing this, right? But we're going to start using if statements to basically have Excel do stuff for us, okay? So we would say something like, if this value is less than 1, comma, tell Excel what you want it to do if that's true. So maybe I want to put the word true. And then comma, if it's not less than 1, I want to put the word false. Now, if I want it to do work, like display a word, I have to put it in quotes so it recognizes it as characters. But we can start to do things like that. And we'll start, that's really the most of the extent that we'll use it in this class. But you could use it to do a lot more things. I might show you a couple things we could use it for, but not expect it necessarily out of you. But yeah, if you do these different combination of if statements to like add these column headings to your row headings so that you're looking up different Z values and you're just using that norm.s.dist, you can actually reproduce the entire kind of standard normal table. Checks out here, sure enough, we get 0.5 at the point of 0. The probabilities just keep on increasing until we eventually get, being 4 standard deviations away, that probability is essentially 1, right? We're out to the 5th or 6th decimal point there of 0.9s. So this is kind of the power of Excel. Like this is like the extent to which you could use it to some, I guess, quote unquote, cool things like this. But yeah, we'll be using that norm.s.dist and the norm.s.inv functions a lot moving forward. When we do confidence intervals and hypothesis testing, we'll see how we can use Excel, and then we'll really be exploiting those 2 functions. So what we're going to do on Friday is think about if we have an exponentially distributed variable, it doesn't look, it's not normally distributed. We'll end up with a distribution that kind of has this shape. We'll talk about how we can use a probability density function for that variable to find the probability of being above or below certain x values. We'll then talk about a real tricky one, which is a log normal, right? So log normal is kind of like a normal distribution, just with an extremely like long but small right tail, okay? And it changes its shape depending on what the variation is. So I say it looks like a normal distribution with a long right tail. If we have, a high enough variance, it could end up looking more like an exponential. So it kind of changes shape. But the interesting thing about the log normal, I just want to introduce it today, and because we'll pick up on it next class, is, so I've got this right here. So what we observe in the data is going to be this variable y, right? So like you can assume maybe we had a data set and I had every single person's test score in here, right? And that's my y variable, right? So that test score is my y variable. And I know that it's log normally distributed, which is saying that if I have some variable x, where x is normally distributed, and my y variable is a function of that, right? Where it's e to whatever that normally distributed variable x is. Well, if we rearrange this to get rid of an e, to get rid of the natural number, right? You kind of take this natural log, right? So what I end up with is a natural log of this y variable, right, is equal to x. Okay? So that's why we say that the variable of test score would be log normally distributed, right?
And knowing this, we can do some rearranging of the, this looks a little nasty, but it's not too bad once we get the numbers plugged in. And because we know that X is normally distributed, we can calculate what the mean and variance for that X variable would be. And then we can just think about, well, now we've got a normal distribution. I can convert that into a standard normal, and kind of now everything just looks like it did before. So we'll talk about those two types of distributions on Friday. Should set us up. That is, and I just remembered that individual assignment after Friday, that will get you through the entire assignment, with the exception of the last question. It's more of like a thought-provoking question as opposed to like doing things in Excel. We're going to start talking about biases, right? So the next thing we're going to go into after this week is, well, this was everything we're doing. We were actually thinking about population distributions. We only see samples. We can, so what's that going to, what problems is that going to cause? What biases might exist? And that's what that very last question of the individual assignment we'll talk about. So we'll probably hit that after fall break. Okay. All right. T's and P's, make it through today. We're almost to fall break. All right, once we get done with Friday, feel a bit of a recharge, okay? We'll see you guys on Friday.